Could we understand dimensions through Eulerian paths? In order to discover the secrets in nature, we have to make a predictive program on the creation and destruction of nature. Nature consists of a structure called fractals and is in a state of chaos, a world of invisible force and rules. We need to achieve a higher dimension to figure out beautiful and mysterious secrets of nature. If we acquire knowledge of humanities through a great amount of reading, we will be able to rise to higher dimensions. Generally speaking, a dimension refers to the maximum number of the coordinate axis within a space that can be independently plotted on. Once the origin is selected on a straight line, a point on the line can be expressed as an x-coordinate. A point on a plane can be also expressed as a pair of coordinates, x, y, by setting a point as an origin and selecting two axes that are perpendicular and intersect at the origin. Here, the straight line one-dimensional and the plane is two-dimensional. Space we usually think of as three-dimensional, and space-time that appears in Albert Einstein's theory of relativity is four-dimensional. To fully comprehend the three-dimensional world that we live in, we need to first understand the two-dimensional world. Solid figures, such as a cuboid, cone, and sphere, have unexposed sides like the back or bottom depending on which way we look at them. This means that we cannot understand them fully unless we look closely by turning them around and flipping them upside down. Even if we were to think only about the physical relationships between various physical quantities such as length, area, time, speed, mass, and force instead of looking at their quantities, we must recognize that each of these has its own dimension. For example, the dimension of area is the dimension of length multiplied by the dimension of length, and the dimension of speed is the dimension of length divided by the dimension of time. Solid figures can be regarded as an extension of plane figures. An accurate understanding of the two-dimensional world would allow us to get a sense of the three-dimensional world more easily. The purpose of studying the two-dimensional world is to better understand the three-dimensional solid figures. By using grids on graph papers, we can draw plane figures more accurately and easily. We can also calculate the area of plane figures without equations if we know the area of a single grid. The reason why we use squares as the basic unit shape for calculating the area of plane figures is that squares can be arranged without gaps in between, and it is also easy to count them. The understanding the structures of plane naturally leads to that of solid figures. 5 different ways to connect 4 dots using line segments of the same length. If we adjust the first figure into an L shape, the dots and lines are connected in the same way although the shape changes. Likewise, the second, third, and fourth figures can be changed so that the lines have different angles, but the connection between the dots and lines does not change. Now, let us extend our thought to a two-dimensional figure, a square. There is only one plane figure that we can make by connecting the sides of 2 congruent squares. If we had 3 congruent squares, we can make 2 plane types of figures, each with I and L shapes. The number of different plane figures we can make with 4 and 5 squares increases to 5 and 12 respectively. By studying the world of dimensions using one-dimensional and two-dimensional figures, we may enhance our feel for figures in the three-dimensional world. To extend the understanding of the connection of segments to that in the world of dimensions, we need to learn about an Eulerian trail developed by Leonhard Euler. An Eulerian trail refers when a path passes through each edge exactly once on a graph consisting of vertices and edges. An Eulerian circuit can be thought of as a one-stroke drawing that starts at a vertex, passes through every edge only once, and returns to the starting point without lifting a pen off the paper. The mathematical term for a one-stroke drawing is the Eulerian trail. The Eulerian trail passes through each edge only once without missing any on a graph of vertices and edges. The picture above is the Konigsberg bridge problem, which is the most frequently cited one-stroke drawing problem. As shown in Figure 1, the Progel River divides the areas into 4 districts A, B, C, and D. Connecting these districts, there are 7 bridges, A, B, C, D, E, F, and G. Is it really possible to cross all the 7 bridges exactly once? To better understand this question, let us draw another picture. If we extend and contract the figure so that each district is expressed as a point and each bridge as a line, we get Figure 2. In Figure 2, A, B, C, and D represent the 4 districts and the lines represent the 7 bridges. The question would be answered if we can start at a random point among A, B, C, and D, draw a trail that passes through all lines only once without lifting the pen off the paper. However, the Swiss mathematician Leonhard Euler proved that answering this question is impossible. Then, what are the figures that can be drawn in a single stroke? If we can draw a figure without going back through the points that have already been passed, such a figure can be drawn with a single stroke. In the picture above, only the first and second figures can be drawn in a single stroke. No matter which point we start drawing from, the third figure cannot be drawn without lifting the pen off the paper. Is repeatedly drawing a figure until we succeed the only way to find out if the figure can be drawn in a single stroke? Euler studied the possibility of single-stroke drawing using the Konigsberg bridge problem and figured out the solution. Euler's method is as follows. 1. Single-stroke drawing is possible when an even number of lines meet at each of every point, that is, every point is an even point. 2. Single-stroke drawing is possible when only 2 of the points are connected to an odd number of lines. In this case, one of the odd points becomes the starting point while the other becomes the ending point. What rules apply to one-stroke drawing? This may sound repetitive, but once again one-stroke drawing refers to drawing a figure made up of only points and lines, moving through each point only once without taking the pen off the paper. Trying to draw one-stroke drawings can have 3 results: drawings that can be drawn starting at any point, those that need to start at a certain point, and those that cannot be drawn with one stroke. In order for the one-stroke drawing to be possible, there needs to be either 2 or no point attached to an odd number of lines. Let us look more closely using the pictures below. The first figure can be drawn in one stroke. This is because all vertices from A to J are even points. In the case of the second figure, the vertex A, D, E, and F are even points while the vertex B and C are odd points. Here, there are only 2 odd points, which means that the one-stroke drawing is possible. However, because vertices A, B, C, and E are odd points in the third figure, the one-stroke drawing is impossible. Let us try to draw the figure above starting from a random point without backtracking the points we have passed or lifting the pen. If we did not understand the rules of the one-stroke drawing and just kept trying hoping for luck to succeed at some point, we would go through multiple failures. To solve the given problem, we need to understand the even and odd points. A one-stroke drawing has to start and arrive at a point. Any of the points in the figure above, A to F, can be a starting or ending point. However, only points A, B, F, and E can be both starting and arriving points. Point A is connected to two lines that allow the line to come in and go out, and point B, E, and F have four lines that let this happen. Likewise, figures made up only of even points with an even number of lines that come in and leave mean the paths drawn along it can freely come in and leave, allowing for one-stroke drawings. In these cases, the starting and finishing points of the figures are the same. However, the odd points like C and D that have an odd number of intersecting lines can act as either starting or arriving point. Points with three intersecting lines like C and D can be 1. A starting point from which the lines go out and come back and leave again, or 2. An ending point at which the lines return and leave and come back again. As such, in the figures with both odd and even points, a one-stroke drawing is possible only when there are just one starting and ending point. Simply put, only the figures with two odd points can be drawn in one stroke. This is because in the figure with two odd points, one odd point would become the starting point and the other one would become the ending point, thereby making one-stroke drawing possible. If we were to think about a figure with four odd points, however, once we choose an odd point as a starting point, all three remaining ones have to become the ending point, making one-stroke drawing impossible. The figure above only has two odd points, C and D. This means that the trail would be either start from point C and pass the other points and arrive at point D, or start at the point D and arrive at point C. Why is space, a mathematical background, important? Topology is a study of laws found in a relationship between forms and positions of points, lines, planes, and positions in space rather than their quantities and sizes. Leonhard Euler was the first scholar to study topology. He found his academic clues from the Konigsberg bridge problem. In short, topology is a study of a position and form. Space was what allowed us to discover the relationship between sets and subsets. Topological space, although a difficult terminology to understand, refers to the space where a set and subset form various relationships. In Euclidean geometry, two figures that perfectly overlap through rotation, reflection, and translation without changing their form are regarded as the same figure. The relationship between these two figures is called congruence. In contrast, topology considers figures to be the same if we can transform them into the same form through bending, stretching, and contracting them. This the relationship between the same figures is referred to as isomorphic in topology. As the word topology implies, historically, a study of topology began from geometry. Therefore, topology studies the characteristics of figures like geometry. Only the difference is that while geometry deals with the size such as length, area, and angle of figures, topology studies the number of points, lines, and planes, and their characteristics and relationships. The academic background of topology was built by Euler, who first used symbols to represent complex numbers, pi, integral calculus, function, and more. Topology was also the process through which Euler resolved his question about the Konigsberg Bridge in Germany, living space of Immanuel Kant. The Prigel River flows under the Konigsberg Bridge, and there were 7 bridges between 2 islands cut off from the land by the river. Residents of this area wanted to know if there could be a trail that crosses each of the 7 bridges exactly once and come back to the starting point. To this question, Euler answered that there is no such trail. He drew the bridges and land on a piece of paper as people saw it. That is, he moved the real world to the abstract world. Euler pictured the bridges as lines and the lands as points. This shift in thought gave birth to topology. Why is topology a part of the official school curriculum? This is because topology is very useful in our daily lives today. Having originated from one-stroke drawings, topology is widely used in various fields such as subway maps, circuits of semiconductors, marketing strategies, finding optimal travel routes, and more. Topology is also frequently used in physics. We can say that physics is an abstract world that has motion and space as its form. The formalization of physics took place at the end of the 17th century by Isaac Newton. Every change or motion occurring in space is caused by something, namely force. When an object moves in nature and we know the force that is being exerted on it, we can figure out the cause of the motion. Once we know the cause, we may predict the position of the object according to time in the future. Physicists have also adopted a new concept known as energy that can replace the role of force. This has allowed them to use the concept of abstraction to figure out the laws and mechanisms in nature. How do we know that space-time is constantly changing? This can easily be seen by looking at the path light moves in. Physicists used to think that light moves in a straight line. However, in his theory of general relativity, Einstein found that light in the vicinity of massive objects, such as the Sun, bends because the objects cause space-time to warp. Thus, as the light moves along such space, its path also curves naturally. Einstein's theory was confirmed and verified through the total solar eclipse in 1919. We cannot see or touch space-time. However, to the hands and eyes of physicists, they are visible and touchable. There may be changes in the characteristics, but they actually exist everywhere. Quantum mechanics broke the mold of space and physics. Particles can move because of force or energy. The movement of particles is not constant because their energy increases or decreases. Newton believed when distant particles affect each other, the space in between is not impacted. However, quantum mechanics show that space between particles does exist with varying values. Thus, this explains the motion of particles because the space in between particles allows the motion of the particles to change by determining the size of energy and receiving it. The space that was always seen as being empty was in fact filled with matter, even contributing to the creation and disappearance of particles. Physicists took the most advantage of the topological tools developed by Euler and applied it. In order to combine Newton's and Einstein's theories, which acts as a basis in physics, a unique field that interprets space, we have to take a mental journey to an 11-dimensional world. Fortunately, mathematicians who expanded their scope of thinking through numbers and space have already explored the world of higher dimensions. Thus, all that the physicists had to do was apply the theory of space already set up by the mathematicians to the motion of particles. By quickly understanding one-stroke drawing in the abstract world, we can draw the invisible. What would it be like if we could not see the various colors, shapes, and lines in the world we live in? Abstract painting is not meaningless if you believe in the practicality of the world of art. We are at a critical juncture where the social awareness of the abstract world is essential. The abstract world, such as topology, is based on the real world. Now let us talk about the Mobius strip. The front and back of a rectangular square can be differentiated. A point moving along one side of the paper cannot move to the other side without passing the boundary of the paper. One of the most well-known strange and mysterious shapes made by topologists, who believe that figures can expand and contract like a rubber band, is the Mobius strip. The Mobius strip, designed by German mathematician August Ferdinand Mobius, has an interesting characteristic where the inside and outside cannot be distinguished. This strip is a two-dimensional figure made out of only one plane. A Mobius strip is made by making a twist of a rectangular strip and attaching the two ends together. An interesting characteristic appears if we were to draw a line along the strip. As we draw the line, we realize at one point that we are on the other side of the paper from where we started. Also, by following along the strip twice, we return to where we started. The Mobius strip symbolizes an infinite cycle, which is why recycling symbols always take the form of a Mobius strip. The Mobius strip is most efficiently utilized in mills. The machines used in mills have a belt that allows rotational motion. If we were to look at this belt, we find that the strip is twisted at one point. This is because by twisting the strip, all sides of the belt come in contact with the machine, thereby making it last longer. Although we live in a three-dimensional world, we encounter many two-dimensional objects. For examples, photographs, pictures, and maps are all drawn on a plane. However, we think of them as being dimensional. Photographs and pictures depict objects with different shape and color according to distance, so that we can see what is closer or further away. The mountains on maps are marked with different colors depending on its height and often have contour lines to show its approximate height. We can obtain enough information from two-dimensional images of things we have already experienced before. However, there is a limit to how much information we can get out of two-dimensional representations of a three-dimensional object we have never seen before. For example, it took a long time for scientists to discover the double helix structure of a DNA with only the X-ray diffraction photographs. Many biologists argue that the DNA had a triple helix structure, but James Watson and Francis Crick discovered the true structure of a DNA through creative thinking. How much comfort and happiness would the change in dimensions bring to the world? People have to eat to stay alive. However, does all of the nutrients in the food we eat get absorbed into our bodies? Many people certainly believe so. However, according to nutritionist Tony Steer, the idea that we absorb everything we eat just isn't true. While you may have a certain amount of a nutrient within a food, what is actually absorbed may be less. People are only interested in the food they eat, not how it gets absorbed into our bodies. Exact quote. Then, how do we absorb food once it is consumed? The food enters our body through the mouth and travels through the throat, esophagus, stomach, small intestine, then the large intestine. In this process, the body absorbs the necessary nutrients and expels what is unnecessary through the rectum. However, we do not consider the food to be in our bodies as it enters through the mouth and exits through the rectum. The food simply passes through a tunnel connected to the outside, while the body absorbs only the nutrients. This is equivalent to how mathematics express figures as points and lines, creating triangles and rectangles. Picturing the human body as a figure, such as a hollow column or pipe, is similar to thinking of figures in mathematics. Ultimately, this means that the digestive system we believe to be inside our body is actually nothing more than a long winding tunnel that starts from the mouth and ends at the rectum, passing through the esophagus, stomach, and intestines. In other words, the inside is really part of the outside. In 1858, German mathematician, August Ferdinand Mobius, went beyond the hollow column form of a human body and found a way to completely reverse the in and out, beyond just having a hollow column-shaped body. He cut a long strip of paper and made a simple bracelet-shaped loop by attaching the ends together. Then, he twisted one end of another strip 180 degrees and attached the ends, making a twisted loop. He then started drawing a line at the center of the strip. As he continued drawing this line without taking the pencil off the paper, he discovered that the pencil that was originally on the front of the strip is now at the back. Next, he tried coloring the strip. In the beginning, he thought that he was coloring the front side but soon discovered that the whole strip was colored. The common sense that the existence of a top means that of the bottom and that the existence of the front means the existence of the back was completely overturned, creating a world made up only of the front. This is the Mobius strip. This time, let us cut the center of the Mobius strip with a scissor. Instead of two separate Mobius strips, we now have one long narrow double-twisted strip. The contorted world where the outside is both the outside and inside is certainly interesting. Now, could we use both front and back in space, just as we do with paper? An answer to this question lies in a rather unexpected example: roller coasters in amusement parks. Roller coasters start off slowly, but as it picks up speed at one point we discover ourselves hanging upside down and cannot help screaming. The rails of the roller coaster is one big Mobius strip. There is no distinction between the front and back and constitutes of only one plane. During the Olympics, skiers fly high into the sky and do stunts in the air by twisting their body. One of the skills is called the Mobius flip because the skiers move along an imaginary Mobius strip. The Mobius strip was not just made for simple entertainment. The Mobius strip is also widely used in the industry. The belt that delivers the power gained from the engine to other axes uses the principle of the Mobius strip. As seen in the previously mentioned example, if we were to use only one side of a belt, the belt in machines would wear out quickly if only one side of it is used. However, a belt twisted once allows both sides to be used evenly, making the belt last twice as long. The Mobius strip is also commonly used in high-tech electronic circuit components. The structure of the Mobius strip can also be commonly found in nature. Charged particles from space move in a Mobius strip pattern when trapped in Earth's magnetic field, and the structure of protein is also twisted like a Mobius strip. There is a limit to how much information a one-dimensional barcode made up of black lines and gaps can contain. This limit was overcome by a two-dimensional code made up of a grid pattern. The QR code commonly seen today is also a type of two-dimensional code. QR is an abbreviation for quick response. The QR code was developed in the mid-1990s by Denso Wave, a subsidiary company of a Japanese automotive manufacturer Toyota, for logistics management. The developers refused to apply for a patent, allowing its use in various fields all around the world. Traditional one-dimensional barcodes can only store up to 20 numeric characters. On the other hand, a QR code can store up to 7,089 numeric characters, 4,296 alphanumeric characters, or 1,817 Chinese characters. In addition, it has better recognition speed, higher restoration capacity than regular barcodes. Barcodes are usually used to calculate products or manage inventory, while QR codes are used more for marketing or delivering messages. Also, because specific scanners were required to gain information from barcodes, consumers could not access it. On the other hand, we can use our smartphones to get information about a product when we use QR codes. For example, by scanning a QR code of a movie poster on the street, you can see not only its trailer but also information on the actors and movie theaters that screen the movie. Department stores and discount stores provide coupons and announcements about events through the QR code. There is even a company that engraves QR codes on tombstones so that people can see the pictures and biography of the deceased. We can effectively organize and analyze data using two-dimensional arrays. For example, it is both inconvenient and difficult to do an overall analysis of test scores if we were to make separate tables for students and subjects. By using a two-dimensional array, we may organize the scores so that it is easy to see at a glance. Excel programs use two-dimensional arrays. We call programs that have been developed to help users calculate, find and manage, and create graphs of data they entered efficiently. Excel, a spreadsheet program designed for computers, is commonly used for corporate tax calculation, reports, grade administration, and ledgers.